This is an AIPMT question in concept of work power energy, because we are going to use conservation of energy to solve this problem. Let's read out the problem. A stone is tied to a string of length L and is held in a vertical circle with the other end is string to the center. At a certain instant of the time, the stone has the lowest speed. At the lowest speed is u. Let me draw for a while before going into further. Let me draw that part. The stone is moving in a vertical circle, say in an anti-clockwise direction. Any direction is fine. At the bottom, it has a velocity u. The length of that, the radius of the circle is L. This is the center. What is the magnitude in change in velocity when it reaches a position when the string is horizontal? You mean to say the string has reached from there to this position, horizontal. At this point, velocity is tangential. Let this velocity is v. He is asking what is change in velocity, v minus u, of course, magnitude. For that, first of all, I need to know what is that v itself. Let us consider a string. At the end is having a stone whose mass is m. When it is at the bottom, when stone is at lowest point, that lowest point itself is a reference line where potential energy is 0. The total energy is potential energy plus kinetic energy. Potential energy is 0. Kinetic energy is half mu square. So there the total energy is half mu square. Now it has gone to the horizontal. So we can say at horizontal, let's assume it has a velocity v. Total energy is again potential energy plus kinetic energy. Being at this position, with reference to this line, it is at a height L, so it has a potential energy mgl. Kinetic energy half mv square, assuming that velocity is v there. As energy is conserved, total energy in bottom equal to total energy in the horizontal position. So what we can say, as total energy is always constant, equation number 1 equal to equation number 2. Equation number 1 is half mu square. Equation number 2 is mgl plus half mv square. We want the value of that. So anyway, we can cancel 2, then it becomes u square. Sorry, I have missed something. Yeah. Multiply that with 2, then it becomes u square. This 2 will get cancelled. Into 2, it becomes 2gl plus v square. It implies v square equal to u square minus 2gl, or v equal to root of u square minus 2gl. This is the velocity at horizontal. But this is not what we want in the problem. What we want in the problem is change in magnitude of velocity. Change in magnitude of velocity is v bar minus u bar in magnitude. These two are the vectors, so I can use parallelogram law. Root of v square plus u square minus 2uv cos theta. Because it's change, a minus comes. It's a resultant, I could have got written a plus. But anyway, between u and v, if we extend, the angle is 90. So that is root of v square plus u square minus 2uv cos 90, that is 0. It's simply root of v square plus u square. I know the value of v, this one. So v square will be this much. U square minus 2gl plus u square. So your answer is root of 2u square minus 2gl. 2 can be taken common. 2 of u square minus gl. That's the change in velocity. That's the answer for the problem. So to solve this problem, we have used a very simple concept of conservation of energy, that when there is no loss of energy, as it is Not mentioned that there is nothing like friction or anything is available. Total energy of the system is constant at all points. At the bottom, whatever is the total energy is the total energy at the top.